Good morning, students. Let's continue the chapter thermodynamics and let's continue the classification of thermodynamic processes. We have seen the thermodynamic process in detail, the isothermal process, the isobaric process, the isochoric process, and now let us see the adiabatic process. In the adiabatic process, the state variable heat is constant. In adiabatic process, heat is not enter in the system or heat is not leave from the system. Meaning is that cylinder is uh, surrounded by some insulating material. That insulating material does not allow the heat to exchange between the system and the surrounding. So if there is change in state, then there is change in internal energy and the work is done. If the internal energy of system is increased, the negative work is done, means the work is done on the system. And if the internal energy of system is decreased, then the work is done by the system. So in adiabatic process, if the temperature is get increased, then work is done on the system, and if the temperature is get decreased, then the work is done by the system. Meaning is that when there is expansion of gas, then the work is done by the gas, the work is done by the system, and then in that case the temperature is get decreased. Now let us see here the PV diagram. This is the pressure axis, this is the volume axis, and suppose this is the initial state. Now the final state, in the final state the volume is get increased, means there is expansion of gas. When there is expansion of gas, then this system does work on the piston, and when this system does work on the piston, there is no heat enter in the system to do that work. So that energy is absorbed from the internal energy of system. In the same amount, the internal energy is get decreased. When there is expansion, then the temperature is get decreased, the internal energy is get decreased. And suppose if we go in this way, that there is the compression of gas, the volume is now get decreased, then the work is done on the system, and when work is done on the system, then there is increase in internal energy of the system. So these changes are made in this adiabatic process. For this adiabatic process, we are having an equation P into V raised to gamma is equal to constant, where this gamma is the adiabatic ratio. From this equation, we may say that this constant C is equal to P into V raised to gamma if the initial pressure is Pi, if the initial volume is Vi. This should be equal to P into V raised to gamma if the final pressure is Pf, if the final volume is Vf. Then this Pi into V raised to gamma is equal to Pf into V raised to gamma. This is our equation A. This is our equation A. Now let us see the work done in these adiabatic processes. The work done, W, is equal to P into dV. This is the work done in an adiabatic process. This is the work done del W. We are interested to find the total work done W. So this W is equal to integration of dW is equal to integration of P into dV. So the limits, they are from Vi to Vf. These are the limits which are from initial volume Vi to the final volume Vf. Now let us substitute this value of P from this equation. What is P? P is equal to C upon V raised to gamma. So this work done W is equal to integration, and the limits of integration are from initial volume Vi to the final volume Vf, and P is equal to C upon V raised to gamma into dV. So the work done W is equal to C outside the integration of V raised to minus gamma into dV, and we know the integration of x raised to n is equal to x raised to n dx is equal to x raised to n plus 1 upon n plus 1. Same thing is here. Here this n is replaced by minus gamma. So we get this W is equal to C V raised to minus gamma plus 1 divided by minus gamma plus 1. So 1 minus gamma, and the upper limit is Vf and the lower limit is Vi. So this is the work done W. This W is equal to C outside the integration. Let us substitute this upper limit first. V is equal to Vf. What we get? Vf raised to 1 minus gamma divided by 1 minus gamma minus V raised to minus V, here Vi, and 1 minus gamma divided by 1 minus gamma. So we get this equation for W. Now we know that this C is equal to what? This C is equal to Pi Vi raised to gamma is equal to Pf Vf raised to gamma. Now let's substitute these values in this equation. What we get? We get W is equal to Vf. Which is the term Vf? Here is the term Vf. So C is equal to, let us substitute, Pf Vf raised to gamma into Vf raised to gamma divided by 1 minus gamma minus this C into this term. Let's absorb this C. C is equal to Pi Vi. C is equal to Pi Vi raised to gamma into Vi raised to 1 minus gamma divided by 1 minus gamma. This we get. Now this W is equal to Pf V raised to Vf raised to gamma, and which is this term here, Vf raised to 1 minus gamma. Actually here is 1 minus gamma minus plus 1 minus gamma. This gamma get cancelled divided by 1 minus gamma minus Pi Vi raised to gamma plus 1 minus gamma divided by 1 minus gamma. Here we get this work done W is equal to Pf. This gamma get cancelled. We are remain with Vf. Vf upon 1 minus gamma minus pi vi, gamma gamma get cancelled, divided by 1 minus gamma. This is the work done. Now for this adiabatic process, the first law of thermodynamics state that the change in internal energy del U is equal to Q minus W, and for this del U is equal to 0, so this Q is equal to W, because here this Q is equal to 0, and so this del U is equal to minus W, del U is equal to minus W, and if we substitute the values of PFVF by applying the ideal gas equation, we get W is equal to N into R Ti minus Tf divided by 1 minus gamma, and this is equal to Pf Vf upon 1 minus gamma minus Pi Vi upon 1 minus gamma. This is the equation. This equation tells us that when the volume is get increased, then the temperature is get decrease, and when the volume is get decrease, then the temperature is get decrease. This is all about the adiabatic process. And now let us see the next process, that is the cyclic process. The next process is the cyclic. Okay, now let us see the next process, that is the cyclic process. Which process is said to be cyclic process? A process in which the system return to its initial state. That process is known as the cyclic process. Now let us see the PV diagram of the cyclic process. This is the pressure, this is the volume. Suppose this is the initial state, this system goes in this way to this point B, okay, and again this system return to the same point. Then this process is known as the cyclic process. In this cyclic process, when the system goes from A to B, then this should be the area under curve. This should be the area under curve. As there is expansion of gas, the work is done by the system on the piston, and when that system return to the same initial state, then in that case this much additional work is done. This much additional work is done, but here the gas is get compressed, means work is done by the piston on the gas. So in this cyclic process, the net work is done on the gas, and that's why heat is get evolved. That's why the heat is get absorbed by the system. So this is the cyclic process. And now let us see the last process, that is the free expansion. That is the free expansion of gas. In free expansion, the example is the puncture of a tire. In free expansion, the heat is not absorbed. The heat is not absorbed by the system. And also in this free expansion, the work is not done on the system. And what is our first law of thermodynamics? That the change in internal energy is equal to Q minus W. Here Q is 0 and this W is 0, therefore there is no change in internal energy. In free expansion, the system gets changed from one state to another state, but there is no change in internal energy, there is no change in heat, and there is no change in work done. Such type of processes, they are known as the free expansion. In this way, we have seen the classification of these thermodynamic processes. I think you got the terms. Thank you.